in 2.1, we're going to first look at linear functions and modeling, and then we'll look at quadratic in the next lesson. So the first thing we're going to talk about is polynomial functions, and the whole chapter is based on solving polynomial functions. We're going to start with the most basic one, like I said, which is linear. So we need to be able to identify what is a polynomial function and what's not a polynomial function. And for something to be a polynomial function, really what needs to happen is your x in the problem there has to have an exponent that's an integer and that's positive. So I guess we should say a whole number for the exponent instead of integer. You can have any kind of coefficient in front there, but this x has to be raised to a whole number value, so 0, 1, 2, 3, something like that. So if you look at these examples, they want us to find two things. They want us to decide, is the function a polynomial function? Then they want to know, actually three things. What is the degree for the polynomial? And then what is the leading coefficient? So they're the three things that we're going to find for each of these. So if you look at letter A, the variables are x squared has a positive exponent, x to the first has a positive exponent, and you have a constant term on the end. You have this square root of 2 out in front, but that's just a coefficient, so that's okay. Makes this thing a polynomial function because all the variables have an exponent that's a whole number, so this is a polynomial function. The second thing they want to know is what is the degree. The degree for a polynomial is just the highest power that x is raised to. It doesn't matter which term it happens to be. This one is the first one. So this would be degree 2. And then finally, the last thing they want to know is what is the leading coefficient. So for that x squared, they want to know what is the coefficient out in front there. So my leading coefficient is square root of 2 for that one. So that's letter A. Letter B, if you look at the exponents for your x, this x has a negative exponent, so this is not a polynomial. Not a polynomial function, so you don't need to find the degree or the leading coefficient because that only pertains to polynomial functions. If you look at letter C, this one the variables have exponents that are whole numbers. However, the whole thing is underneath this square root. So again, this is not a polynomial function. Right, so we don't need to find degree or lead coefficient. And then our last one here, if we look at these exponents for my x is raised to the first, x is raised to the fifth, those are whole numbers. I have a pi out here, but that's just a constant term. That's okay, it's not an exponent for your x. So this one is a polynomial function. So the degree for this one, we're looking for the highest power of x, which is the fifth power from that last term. And the coefficient that's with that highest power of x, that degree, is, be careful, it's a negative 4. So its lead coefficient is negative 4. Even though this last one here is not written in descending order, usually they'll put the highest power for x first and then go down, but they didn't do that for this one. So you'll have a few problems where that's what they'll ask you to do, is determine whether it's a polynomial or not. All right, special types of names for polynomial functions. They just give us a few here. We'll learn some more in the next couple chapters there. So a zero function is going to be something where you just have y equals 0 or f of x equals 0. The degree for that is called undefined because technically you don't have any x's in the problem there to raise to an exponent. So a constant function is y is going to equal some number that's not 0. So, an example would be like y equals 5. And that constant function, if you look at the graph, y equals 5, there it is. Right? It's constant. It's not increasing. It's not decreasing. So they'll call that, they'll say it has a degree of 0. And then the type of equation we're looking at today is a linear function or the equation of a line. So equation of a line will have an x to the first power, and that would be degree 1. And then the last thing that we'll look at actually tomorrow is a quadratic function where you have an x squared in the problem and it's degree 2. And we know the shape for this. This is your parabola. All right, so we're just going to focus on linear functions today. So we're going to look at graphing equations of lines and how do you come up with the equation of a line and things like that. So we have a few formulas that you need to know. And you just need to know these. There's no formula sheet for it. You just have to recognize it and understand it. So the first one, to find the slope of the line, it's just your change in y. You may or may not have seen that little triangle symbol before. That means change in y over change in x. You might also have said rise over run. And what you're looking at is 2 points on a line, and what's the steepness of the line is what the slope is. It's also a rate of change. When we start applying this in application problems and in calculus, you'll see that the slope actually represent a rate that something is changing. Oh, here it is in the second bullet line here. All right, so rate of change is just the slope. So you have a couple of ways, 3 different ways that you can write the equation of the line. You're probably most comfortable with slope-intercept form, y equals mx plus b, which is fine. In calculus, we use this point-slope form a whole lot because that requires sort of less algebra. If you're given a point and a slope, you can write the equation of the line. You don't have to bother to solve for the y-intercept, which a lot of you will end up doing there. And then the last one, standard form, this one is kind of the old school form where it looks really nice, but it's not super helpful in terms of trying to graph this. So things about this standard form, let's see, A and B and C all have to be integers. So no fractions, no decimals. And this Lie coefficient A has to be positive. So if it was a negative value, you'd have to divide everything by -1 in order to make it a positive value. If you have an equation that's in standard form, I'll just throw this in here too. You can find the slope instead of solving for y equals, instead of putting it back in the slope-intercept form. The slope is just the opposite of your coefficient for x, which is your a, over the coefficient of b. That's kind of a nice, quick little formula that if I gave you an equation like 2x plus 3y equals 4, you could find the slope of that. Negative a over b, so negative 2 over 3. It would be the same as if you solve for y equals, but that's just kind of a nice little shortcut. I don't remember if it's in this textbook or not. All right, so some of the problems that you're going to have to do, write the equation of a line. So it says it's a linear function, and you'll notice that the points that they give us are all in function notation. So function notation, when x is 3, this is our x value, our y value is 5. So you can write that as a coordinate pair. So when x is 3, y is -5, which is probably the way you're used to seeing it. And then same with this one, when x is 6, y is 2. So if I'm given 2 points, I can find the equation of the line by finding the slope. Let's find slope first. So it's y2 minus y1 over x2 minus x1. And you can call whichever point you want x1 and y1, x2 and y2. It really doesn't matter so long as one point is both the 1s and the other point is both the 2s. So if I follow y2 minus y1, that would be 2 minus -5. x2 minus x1 would be 6 minus 3. So I get a slope of 7 over 3. Now if you go back up and you use your slope-intercept form to find the equation of the line, y minus your y coordinate equals the slope x minus the x coordinate. I can pick one of these 2 points, whichever one I like, and I can plug that in for x1 and y1. I guess I'll use the first point just because that one's labeled x1 and y1. So I would say y minus the y coordinate is -5. The slope I just found was 7/3. And then the x coordinate, x1, is 3. I'm going to get the same equation if I plug in 6 and 2 if I simplify it. When it's unsimplified, it doesn't look the same. So I can leave this way. This is my point-slope formula, point-slope form for the equation of the line. If I don't want that form, if I want to put it in a different form, I could take that equation right here, and I could just solve for y. So if I distribute the 7/3 through the parentheses, And that 7/3 times that -3 would give me -7. And if I solve for y, I'm going to get 7/3 x minus 12. And this is my slope-intercept form. Right? Either one is acceptable. They both have the same meaning. The only difference is sometimes the directions will tell you specifically which form to put that in. And I guess while we're at it, we could, I'm just going to erase some of this, I have a little bit of space here. If I want to put this in standard form, this last form that we're looking at here, the ax plus by equals c form, I could just take this equation then. I'm just going to move up here. Right, and I want the x on the left, the y on the left, so I'm going to subtract 7/3 x from both sides. And then I can't have any fractions, so to get rid of the fraction, and also this negative as well, because we said this a value has to be positive and no fractions. So if I multiply all of my terms times a -3, that's going to give me 7x minus 3y. And if I multiply this side by -3, I'll have 36. So now it's in standard form. So all three of these equations are all in the equations of the same line. They're just written in three different forms there. All right. I'm going to erase this, so if you're not finished copying it down, make sure you pause. All right. All right, and then the third example here is just a word problem. So if you're trying to find the equation for this depreciation for this car. So you purchase a car for $30,000. So when time is 0, the cost of the car is $30,000. And then what happens is 5 years later, now the value of the car has depreciated. Now it's only worth $12,000. So they asked, what's the rate for depreciation? And we said rate is just the slope. So if I find the slope of this is really just 2 points. All right, we'll do t comma c is what we're looking at. So 0 comma 30,000. And then the other point is 5 comma 12,000. Put that comma in there because it makes it look confusing. All right, so if we want to find this slope, which is the rate, it's going to be my y minus my y coordinate. You can subtract in either order. I'm going to start with the top point first and subtract the bottom point. So now when I subtract my x's, I need to go in the same order. So 0 minus 5. And 30,000 minus 12,000, that'll give me 18,000 divided by -5, which is -3,600. So this is the rate that the car is depreciating. And if we want to put some units with it to make sense, it means that the car is depreciating at a rate of $3,600 per year. So it's going down, so you could say it's negative $3,600 per year, or you could say it depreciates by $3,600 per year. And then they want us to come up with the y-intercept. So let's write the equation for the line. So if I want to find the equation for the line, I have the slope. I'm going to take one of the 2 points. Now one of these 2 points is going to be easier to work with than the other one. And it's going to be this first point's easier because you have an x-coordinate of 0. So if you think of your y equals mx plus b, we'll use that form because I'm looking for what the y-intercept is. We might as well put it in that form. So if I plug in my x and my y coordinate, I know we call them t and c, 30,000 equals my slope, which was -3,600, times my x coordinate, which is 0, equals b. So my b, or my y-intercept, is 30,000. So the equation for the line is this: y equals my slope, -3,600, x, plus my y-intercept. Or if we want to write it in terms of t's and c's, I guess we could say the cost with respect to time would be negative 3,600t plus 30,000. If either one is the same thing, just depending which variable you want to use. And then it asks, what does this y-intercept mean? What does it represent in the problem? The 30,000 was the initial value of the car. How much was the car worth at the very start? All right, so you're going to have to write some equations of lines and find some slopes and rates of change. The last thing that you're going to have to do is look at scatter plots, and we'll go through and put them in the calculator and come up with some equations using the calculator. So the first thing that you're looking at is when you graph a scatter plot, when you plot your points, I usually put it like this kind of circle around your data there. And what you're looking for is how thin is this circle. The more narrow it is, the more it looks kind of like a pencil, the stronger your correlation is. The wider the circle, the bubble is, if it looks more like a circle, then you really have no correlation. Whatever this is and this represents, they really have no correlation to each other, no relation to each other. If your bubble is sort of going up from left to right, then it's going to be a positive correlation. If it's going down from left to right, then it's going to be a negative correlation. And these say linear because it's in the shape of a line. You can have scatter plots that are different shapes. They might be sort of curves, they might look like a parabola, and we'll go through and look at those tomorrow. So there's a couple things that we're going to put in your calculator. So you need your graphing calculator out, so you can pause and find it if you don't have it out yet. One thing we're going to turn on is this correlation coefficient. And this only works for linear equations. You'll only see this value. When we do scatter plots for quadratics, it won't pop up. But this correlation coefficient, this R value, what it tells you how strong this thing is going to be. How tight are these points going to be? Are they going to be real close to being a straight line? Or are they going to be sort of scattered a little bit? Or are they going to be real wide? So the closer this R value is to 1, you're going to have a much stronger correlation. If it's real close to 0, then your data is going to look like this, like a big bubble, and it won't have any sort of correlation. So that value, you don't have to calculate, it will pop right up on your calculator. If that R value is positive, then your graph is going to look like this, going up in the positive direction. If that R value is negative, then your data is going to be going like this, going downward in the negative direction. Pearson product moment, R squared, this is a value that will pop up for more of our correlations that we'll look at. And what it does is it takes that R value we just talked about and squares it, which will make it positive, which makes it a percent. What it means is if you get an R squared value of 99, it means 99% of your Y values, whatever it represented, is directly attributed to the X values. So for our car example, we would say if we got a R squared value of 0.99, it would mean 99% of the value of the car is directly related to the number of years, the age of the car. So it just gives you sort of the strength of the correlation, gives you a numerical value to look at to sort of think about that. All right, so we're going to do this example. You need your graphing calculator. I have my data typed in here, but I'm going to show you where to go and what to turn on for your calculator so we can make a scatter plot. You could graph this by hand. You can, put your axes here. We're going to graph it in the calculator and then come up with the equation using your calculator, and then we can do a prediction using using your calculator. All right, so pull up your calculator. I'm just going to kind of split screen this here so you can kind of see both. There we go. All right, so in your calculator, there we go. Now we can see all the data. In your calculator, your blank home screen, you're going to go to the mode button. And the mode button is, stat button, which is right here. We're on mode right now. It's diagonal from it. So when you hit that, we're going to go into number 1, which is edit your list, and hit enter. And now you're going to go over to list 1. If you have data in here, you would hit the clear button and you would hit enter. Clear and then enter, and that'll clear out any of the data that's in there. So here, I'll show you on list 3. If I had, some data in here that I don't want, go to the top of the list, hit clear, and hit enter. And it'll just get rid of the data there. If you hit the delete button, it gets rid of the entire list. So you wouldn't even see list 3 on the data there. All right, so go over here. You're going to type all of the time values into list 1. You're going to type all of your distances, into list 2. Once you have that typed in there, you can jump ahead to where we're going to be. So if you need to hit pause, you can type that data in, hit pause. I'm going to keep going. So now what we're going to do is we want to come up with the equation of this. And we'll make a scatter plot and everything as well. So if you look at your x values, some good increments for your x values, looks like the lowest value is 1 and the highest value is 15. So when you make your scatter plot by hand, I would probably list these all by 1s. All the way up to 15, and this is going to represent your time in seconds. And then your y values are your distances, and it was measured in, looks like meters or centimeters, I can't see, centimeters, all right. So my y is measured in centimeters. All right, and if you look at your y value, so we can kind of see what we need to go from and to, looks like our smallest y value is 5 and our biggest y value is 90. So maybe you want to go up by 5s as you go through and you label this, and so on. I'm not going to label all of them. I think you can plot points at this point. So with your calculator, we're going to come up with the equation of the line. But one thing you want to do before we do that is we can go in and we can set up so that the calculator will, phone keeps ringing, sorry, so that the calculator will give us that r and that r squared value. So we're going to go into the second and the 0 button, which is the catalog. Now this gives you an alphabetical listing of everything that's in the calculator there. So we want to go to D, which is diagnostic. So we're going to hit this, let's see if the D button will work for us. So if you hit the X and the -1, you can see the D is in green. We'll take you to the beginning of the D's. And we're going to just arrow down till we get to diagnostic on. Hit enter and hit, oops, oh crap. So you're going to hit enter twice once you get to there. This didn't work for me. Too many distractions. All right, we're good. Enter, and then hit enter again. It'll tell you done. It doesn't do anything, but it will do something. You just turned it on in the calculator. All right, and then you can do second and quit or clear, and then we're going to go back into that stat button. So everything we're going to do is in stat. If you go over to the calculate menu, the second menu over, we're going to go down here to number 4 where it says linear regression, AX plus B. So you can just hit 4 or you can arrow down. Now it gives you the data's in list 1 and list 2. Just arrow down to calculate and hit enter. And then what it gives you is the equation of this line. So this is our answer for down here. Y equals, they use A for the coefficient, 3, 5. We're going to round to 3 decimal places. And then my B value is -4.676 if we round to 3 decimal places. They also give us this r squared value right here. So 91% of the distance that was traveled is directly related to time as opposed to something like friction or something like that. And your r squared value is 0.95, which is really close to 1. So this is strong. It's a strong correlation. When we do our scatter plot, all of our points are going to be pretty close together. And it's also positive, so it's going to be going up from left to right. Once you have the equation, let's move this out of the way. Once you have the equation, then we can I'm just going to rewrite this equation down here. We can do this prediction here. So we're trying to predict, here's my equation, 5.357x minus 4.676. Now I can get rid of this other stuff here so it's not distracting me. There we go. And they said, how long is it going to take to travel 137 centimeters? So remember, your y-axis was your distance. So that's what my y is equal to. So we'll plug in y as 137. Oops, I have these backwards. 357x. All right, and then you're going to add your 4.676 to both sides. All right, and then so on, and you're going to get your value for x. And you can kind of look at your data, 137. If we had a list that was pretty big that showed that value on there, you can kind of see that it'll follow along, along this line here. I'm not going to finish that. You can finish solving this little equation here. That's not too bad for you. All right, so you're going to do then for tonight for homework in your textbook, you have page 169, 1 through 11, the odds, 45 to 49 all, and then 51 and 52 and 53. These, I believe, are all the scatter plot problems. The other ones are finding the equations for lines and slope and that sort of thing. All right.